transformations for matrices. So like I was saying, this is often taught in like Algebra 1. It's super simple. Way simple for a pre-calc. So if we have a square that looks like the square that we have, and we have the corner points 4, 8, 4, -3, -6, -3, and -6, -8, we write all of those points vertically. So we would write all of these points like that, okay? And we're going to talk about how they're transformed, okay? And it's really easy. If you're going to add 3 to each x value and 4 to each y value, we want to know what happens to the square when we do that, okay? So if we had all of these are all of my x values, right? What do you do to all the x values if you're going to the right 3? Do they get bigger? Do they get smaller? They get bigger. So we're going to add 3 to all of those values, right? And then it says, what would that do to, and then 4 to each y value. So for those, we're going to add 4. So where does the square move? It moves right 3 and up 4. Is it still a square or is it a rectangle? What is it? It's still a square. It doesn't change. Does that make sense? Okay, so if we were doing that, basically we're just taking each of those points and we're adding 3. And then we're taking each of the points y value and we're adding 4. Clearly, you can do this without writing all of these steps, correct? Yep.
Why is there an 8 and -8 for y values?
An 8 and a -8. Oh, should this be a +8? Did I put the wrong thing? Let's see, -6, (8), and -6, -3. Yeah, that should be a +8.
Good job.
Thank you. All right, so what does that do to the square? It moves the first point to 7, 12. It moves the next one to 7, 1. It moves the next one to -3, 1. And the last one to -3, 12. So all of those points have moved. Okay, pretty easy to do by hand. Okay, obviously there's shapes that are more complicated than squares. So there's something that people use every single day, and Ben, you were asking me about this the other day. Why do we need matrices? Just what everybody asks for every topic in math class. Okay, some of you may not use matrices at all after pre-calculus. Some of you are going to use it every day. My brother is the vice president for Voya. You know those commercials, Voya? It's like the former ING. And he uses matrices every single day because he's in finance. And they use Microsoft Excel. Do you guys know what Microsoft Excel is? That's a giant matrix. So when it says A1, B1 or whatever, it's row A1, column B1. I mean, do I need to open it up? Do you guys know what I'm talking about? Microsoft Excel? So you probably don't know Microsoft Excel. So it looks like this, right? This is one. How do you not see that it's a big matrix? What if I had all of these? Right? Row 1, column 1. All of this is a matrix.
So like your x and y values, instead you have like 20 x values?
No, it's just like you can set up your different, if let's say I had all these scores for a test, 74, 59. I can put all of them in here. Do I need more 95s? You're feeling bad about these?
Yeah.
I always have this person that gets all of them right and a bonus. All right, so anyway, if I wanted to find like the average, what you do is you put into Microsoft Excel, average, parentheses, and then it says this matrix, right? And you hit enter and it gives the average. So there's tons of things you can do in Microsoft Excel. So that is a giant matrix. So it's important that we know what operations to put in. So we could have a whole bunch of points, as Julia is saying, like I could have like 100-sided figure. I mean, we don't use it for geometry typically, but I could have a 100-sided figure and all these different points, and I could say, okay, for all of my x values, I want to add 3. For all of my y values, I want to add 4, and it would do it for me right away. Does that make sense? Fun. All right, so these ones that I'm giving you are not hard to do by hand. You don't need Microsoft Excel to do this. So number 2, it says multiply the entire matrix by 2 and then sketch a graph of the resulting points. What did this do to our square? So if we multiply the entire matrix by 2, so let's say we start with that original 4, 4, -6, -6, 8, -3, -3, +8, right? Because Kyle corrected me. Kyle gets a bonus point. And if we have this number out front, it's called a scalar. Do you remember that? and we just multiply the scalar into everything. It's like saying I take our matrix and we add it to itself. All right, so when we do that, we get 8, 8, negative 12, negative 12, 16, negative 6, negative 6, 16. And think about what that does to our matrix. So we have 8, and then we have negative 12. And then we have, oh, what am I doing? 8, negative 12. What am I talking about? 8, 16. And then we have 8, negative 6. And then we have negative 12, negative 6. And then we have negative 12, 16. Okay. What happened to our square? What do you guys think? It doubled what? It doubled, well, kind of. It's actually ends up being 4 times the area. Kind of weird. But it doubled the size. Like it doubled the length and the width, right? Does it make sense? So I shouldn't really say area. Yeah, so it became twice as big. We call this a dilation. A dilation by 2. So the length was multiplied by 2, and our height was multiplied by 2. All right, so what if I multiplied our matrix by 1, 0, 0, negative 1? Okay, so let's write down the matrix again. So I have 4, 4, negative 6, negative 6. 4, 4, negative 6, negative 6. And I have 8, negative 3, negative 3, 8. Okay, this is, what's the dimensions of the matrix that I just drew? How many rows, how many columns? 2 by 4. So if I'm multiplying, do I put it here? Can that work? No. So where do I have to multiply it by? I have to multiply it in the front. So I'm going to do 1, 0, 0, negative 1. So I do a 2 by 2. I always set mine up the wrong way, and then I'm like, oh, I have to erase. All right, so rows, columns, and we multiply. I'm going to get a resulting matrix that is still a 2 by 4. Which makes sense because it's just telling us where our points have moved. We're still going to have 4 corner points. All right, so the point that was 4, 8 is going to move to 4, move your fingers, 0. 4 plus 0 is 4. Do you want me to write out the 4 plus 0, or should I just write 4? You guys remember how to multiply? There, and then we move here.
0 times 8.
Yeah. All right, the next one. We're going to do 1 times 4, and then we're going to move our fingers. 0 times negative 3. So again, we're going to have 4 plus 0. The next one. Oh man, I'm going to get messy here. Let me get rid of my red ones here. So the next one, we're going to do 1 times negative 6 is negative 6. Move our fingers, plus 0. And we do negative 6, or 1 times negative 6 is negative 6 plus 0. The top row is identical. We did not change anything on the top row. I'm guessing the bottom row probably changes. All right, the bottom row, I have 0, 4. 0 times 4 is 0, added to negative 8. So 0 minus 8. I get 0 plus 3. Are you guys following all these numbers? I get 0 plus 3. And I get 0 minus 8. So the bottom row becomes negative 8, 3, 3, negative 8. So what is different about my first matrix, the 4, 4, negative 6, 8, negative 3, 8? What changed? The signs of which ones, though? The y values, right? So our y values changed. So they became the opposite. Okay, so let's think back to our transformations. If your y values become the opposite of what they were, what kind of transformation is this? It's a reflection over what? Ah, good. Yeah. Alessandro's saying like this. He's moving his hand like this, right? It's going over the x-axis. Exactly. It's going to flip it over the x-axis. So this ends up being a reflection over the x-axis. Over the x-axis. Right, because our y values became the opposite of what they were. So if you went back to our main picture, this picture right here, basically these points up here are going to move down, and these points right here are going to move up. So our square will end up being like right around here. And you guys can sketch it out if you want to. But it will just end up reflecting over that axis. So all the y values will become opposite. All right, so when you look at that, if I asked you to reflect a certain matrix over the x-axis, you would multiply it by 1, 0, 0, negative 1. Okay, it looks like the identity matrix. Do you guys agree? Except that y value in the corner is a negative 1.
So how do we know that it's not just like down 5? Because it doesn't flip the mirror image.
Yeah. Because every point is now switched to its opposite. Yeah, it could look like it's down 5. In this case, we had a square. But if we had any other shape, you would definitely see the reflection, right? Like, imagine you have a triangle. Like a triangle like this, then it would definitely go that way. It would flip over. All right. Next up. So you have a big chart. If I put this on your test, you'll have the big chart. Very nice of me, right? And so it's telling you what you're going to do each time you have some kind of transformation. So we can dilate or compress. Compress means make smaller. An image by a factor of k. So we do that by multiplying by a scalar. Number 2, you can shift the unit right h units. So you would add h, the x values. If you shift it up k units, you would add k to the y values, and so on. Okay, so 4, it says reflect the image over the x-axis. That's when your y changes, so this one's a negative 1. But if you reflect it over the y-axis, that's when your x changes. That one's a negative 1. So just remember, it looks like the identity, but one of them is an x value, one's a y value that you're switching. And then if you reflect the image around the origin, remember that's a rotation. So if you had like a triangle like this, you would rotate it around the origin 180 degrees. Gosh, now I gotta like think about what that looks like. I'm going to use my handy dandy tool. If I rotate 180 degrees, it's going to look like that. Does that make sense? So now I got to remember what it looks like because you can always switch your paper around too. So when I draw it, it would look like that. All right, and then reflecting the image over the line y equals x. Why would that be useful to us, reflecting over the line y equals x? Do you guys remember what reflects over the line y equals x? These are inverses of each other. Okay, so an inverse of each other would, I don't think that's exactly how it looks, actually. I think it would be the other way. I think it would look like this. So if you fold the line, if you fold over that fold line, the y equals x, you would get the same thing. So we would use that if we're trying to find the inverse of a function. Does that make sense? All right, so next up. So it says write the new coordinates of the transformed trapezoid using the original trapezoid on the right. Graph to check if needed. So this is what your homework is. It's really not that bad. Okay, so we're going to find these points for the trapezoid first. So the point A is going to be negative 2, 4. The point B is 2, 4. The point C is going to be 4, 2. And the point D is going to be negative 4, 2. So I'm going to write those in order, A, B, C, D. So I'm going to have negative 2, 4. I'm going to have 2, 4. 4, 2, negative 4, 2.
Out of the order.
No, I just typically will put them in alphabetical order. And if we're reflecting over the line y equals x, if we look at our handy dandy chart, it says that we just basically, instead of having the identity, 1, 0, 0, 1, we switch our zeros and ones. Oops, I had that on the wrong side, I think. Man, I do have these on the wrong side. I thought I fixed this image. This should be over here. This should be over here. Is that correct in your notes?
No.
Yeah, I think I made a mistake. And then I told Mr. Clark to correct it because he had not printed his yet, but I did not correct ours. So we end up putting these in the front. So on your study guide, I have this chart again, and it's the correct way. So just put your 1, 0, 0, 1. Because you got to multiply it in front in case you have, like, remember I said if you had like a 2 by 4, you would need that like we did earlier. All right, so we're going to do 0, 1, 1, 0. And we're going to multiply it out. All right, any ideas on what you guys think is going to happen to these points? If you reflect over the line y equals x, yeah, they switch. The x and y values are just going to switch. Okay, so you could really be cheaters on your homework, and I would never know that you didn't actually multiply because you could just be like, oh, it's going to be 4, negative 2, 4, 2. Does that make sense?
So we can't cheat on it.
You can. It's fine. All right, this is why this is like taught in Algebra 1. It's like taught before all this. Like you learn all this stuff. All right, so you're going to have 0 times negative 2 becomes 0. Added to 4, we get 4. And then we have 0 plus 4 is 4. We have 0 plus 2 is 2. We have 0 plus 2 is 2. And then we go to the bottom row. Negative 2 plus 0 is negative 2. 2 plus 0 is 2. 4 plus 0 is 4. Negative 4 plus 0 is negative 4. See how they just switched? All right, and then you can graph it and you can check, but that will end up being a reflection over the line y equals x. So we're going to have like 4 comma negative 2. We're going to have 4 comma 2, 2 comma 4, and 2 comma negative 4, which the reflection over the line y equals x is always hard for people to visualize. But imagine folding your paper over that line. Do you see how they would become the same image? That's what's happening. And typically when I label this as A prime. This is B prime, C prime, D prime. Okay, so it means it's the point that correlates with A, right? Corresponds to A, I guess. All right, so let's try the next one. So what if we compress it by 1/2 unit? So what would we do if we're going to compress something by 1/2? Just multiply by that scalar out front, right? Does that make sense? So we have, let's see, negative 2, 2, 4, negative 4. And then what do we have? 4, 4, 2, 2. So we're just going to end up doing 1/2 of that. So super simple. We just get negative 1, 1, 2, negative 2, 2, 2, 1, 1. Do we like this section? You're like, oh man, we need easy sections like this all the time. All right, reflecting over the x-axis. Okay, it kind of looks like the identity. But when we reflect over the x-axis, what changes? Y. So instead of having 1, 0, 0, 1, we have 1, 0, 0, negative 1, because we want to change our y's. So that last spot changes the y's. And we multiply. Can we be big cheaters? Yes. What's going to happen? The top stays the same. The bottom becomes negative 4, negative 4, negative 2, negative 2. It becomes the opposite. Now I would maybe check your setup and check maybe the first couple, right? And make sure you're right, but we are correct. All right, and then this one's a little bit different. We're shifting right 5, down 4, and then we're reflecting over the y-axis. So I would do a couple steps at a time. Like I'm not going to do all of it all at once. So if I have negative 2, 2, 4, negative 4, 4, 4, 2, 2. If I'm going to shift it right 5 and down 2, how will I adjust my x's and y's? I'm going to add 5 to the x values. I'm going to subtract 2 from the y values. Okay, there's not a super nice way of writing this. We'll just do that operation. So when we do that, we're going to add 5 to each of them. So negative 2 plus 5 is going to be 3, 7, 9, 1, subtract 2, 2, 2, 0, 0. You got that? So that moved it.
And the last question, with the last number on the x being negative.
Yes, thank you. Negative there, thank you. All right, so now we're going to reflect it over the y-axis. So let's go ahead and write this again, and we're going to put a matrix in front of it. So we're going to put the matrix reflecting over the y-axis changes what value? the x value, yep, the one on the top, so negative 1, 0, 0, 1. Okay. So as we write that matrix, we could multiply it all out. All right, and you can check, when you multiply it all out, the top row is going to change, right? It's going to become negative 3, 7, or negative 7, negative 9, negative 1, and then 2, 2, 0, 0. That's our resulting transformation. And you can sketch that out, okay? You can sketch all of those new points, and you will see that it is just that trapezoid that's been shifted right 5 down 2, reflected over the y-axis. Okay, so see how this could be useful learning things like this if you have a very, very complicated shape. Okay, a four-cornered one is not that hard to do. But if you had a whole bunch of corners, it would be very useful, and a whole bunch of operations too. All right, so what's the point of all this? So basically we want to be able to rotate shapes, and we want to rotate it by any angle, okay? So this leads to really cool things like graphing conic sections that have been rotated by a certain number of degrees, like 12.2 degrees, right? So for example, the two ellipses shown are identical, except one has been rotated by pi over 6, or 30 degrees. Do you guys see it? Look at their equations. They're very different, aren't they? All right, you could get this by graphing in Grapher. Grapher's on your computer, but you would not be able to graph this one on your graphing calculator very easily, because it's hard to solve for y, like how to get the y by itself. You can, there's methods, but. Okay, so it says, notice how the second equation has an xy term. This is an indicator that there is some kind of rotation of a conic section involved. Okay, so it's going to be something that's not like flush on the x and y axis. Okay, it's moving. You would not be able to complete the square. We're going to learn about this in the next section. So I did this very easy section today, and you get a really hard one tomorrow. It's very exciting.
We don't have math tomorrow.
Oh, not tomorrow, then Friday.
We don't have math.
Oh, wait, what is today? I know, I keep thinking it's a Wednesday because it's a C day, right? So on Monday, we get to do this. Very exciting. I thought about doing it today, but 2 sections for a double. Man, we'll hold off. Huh?
As part of the notes or your homework?
We will be doing that, yeah, like lesson 54 is rotation of conic sections. It's not easy, but that's the last section of this chapter.